All right. So I think most of you saw my email. All of the videos will now be on YouTube. I'll go ahead and do that like after every single session. I'll record it. Probably not immediately, but by the evening you'll probably see it on YouTube because once I get home I'll have to like render it and everything. So that'll be fine. I got a couple more questions about yesterday's homework. Just remember, make sure to watch yesterday's lecture, lecture number 2, before starting the homework because there are some things you'll need from lecture 2. There were a couple questions asking about like the format of the answers. Don't worry too much about the format. I just want to see some answer to the question, right? Like when I say convert between English and quantifier notation or predicate notation, that's exactly what I mean, right? Just, you see those statements, the first 5 or 4 or 5 are predicate, and then the last 5 are English. I basically want to see, okay, rewrite it in terms of one or the other, right? So that's really all I'm looking for. In terms of formatting in LaTeX, if you want, you can format it pretty much like how the question is asked, right? So if you look at the text file, the enumeration, I didn't ever actually write out 1, 2, 3. I just really did. This is just the begin enumerate environment, and then for each one you do backslash item, and then just write whatever you want here. If you want dollar signs, you're still going to need dollar signs. This environment doesn't do it for you. If you're using the equation environment, the align environment, or there's another one I'm forgetting right now, but essentially there's a few environments that automatically assume you're in math mode, but you'll find it out as you go. Because if you have an environment that only accepts math mode and you should put dollar signs in it, it's going to get angry at you. So you'll see it very quickly. Okay, so the idea here is we've kind of finished talking about the grammar, right? So now that we're done with predicate and propositional logic, we've kind of compiled a framework for the grammar that we use. And we're going to keep using these quantifiers, we're going to keep using these ideas, but now that we know how the grammar works, we can talk about objects, right? So we can start building our vocab and building a list of mathematical objects. And so the first one that we should talk about are sets, right? So we'll see if I can fit everything about sets in today, because I don't want to cover too much into set theory, but I want to cover, more than introductory set theory, enough to like talk about the stuff that you guys will need. So maybe at most we'll do maybe a little bit more tomorrow, and then we'll lead into some proof concepts, a lot of which will require set theory. But for now, we'll just see how far we get today. And we're supposed to go, so on the syllabus, I have our meeting time set for 2 hours on Thursdays. So far, I haven't gotten a lot of requests for problem sessions. And we also really haven't done as much material as we need problem sessions. So I'll probably end class around an hour or an hour and a half today. And then I'll figure out I'll send out a poll maybe, and we'll figure out what we need to cover. And then I might just have class meeting on Monday, Wednesday, Fridays. And then until we need problem sessions or something like that. So I'll just ask everyone to send me some opinions on what you guys want to do, and then we can figure it out. But anyway, sets. So as always, a lot of you probably know what a set is, right? A lot of you probably do know the definition, but like I said, if we ever want to start building from scratch, right, we need to define some things, right? So a set is a collection of elements we can extend this definition to say it's a collection of elements that satisfy a certain property I'm going to put a big question mark and a big parenthesis because there's a problem with this part. And we'll talk about this problem in a little bit. Right? For now, we can just think about it as a collection of elements. Some notation, so let's start with that. The way we write a set is this, right? So usually we use capital letters for sets. So maybe I can say A is equal to set. So what this means is A is the set containing the elements 1, 2, and 3, right? So each of these guys is an element. So we can define an element is an object. Now, obviously, there's an issue with these definitions because here I said the set is a bunch of elements. And I said an element is something from a set. So obviously there's some sort of recursion. These are not good definitions, right? But so ignoring this part here, just compare these two statements. Set is a collection of elements versus an element is an object in set. Part of what I want you guys to do is see, so this is a first exercise in thinking about definitions. This kind of gives you, I'm going to kind of give you an idea of what these are. But then I want you guys to try to figure out if you had to properly define these, how would you define it, right? So either you can define an element first and then a set, or a set first and then an element, right? There might be a more natural way to do one of these, but it is doable in both ways. But essentially, see if you can come up with a pair of definitions for a set and element that isn't recursive like the one I wrote here, right? But this gives you an idea of what's going on, right? So we have this. So what's an element of A? 2 is an element of A. Or 3 is an element of A, right? And so the first piece of notation we use to show something is an element is we use this symbol, right? That's not the Greek letter epsilon. It looks similar, but it's not. On LaTeX, this is \n, right? Because it literally just means A is it's in A, right? That's what we say. We say, instead of always saying, oh, this is an element of this set, this is an element of this set, we just say, oh, this is in this set, right? Because it's inside that set, right? So this says A is an element of capital. Just a quick note here. Typically, we use capital letters for sets to talk about sets. And lowercase for elements. Obviously, it's not a hard and fast rule. You're allowed to pick whatever letters you want. You're allowed to pick whatever variables you want to represent anything you want, which is fine. But generally, in math, we're going to try to pick different types of letters and different types of notation, just so that when we are looking through our notes, we know what something is immediately looking at it, right? So if we have this kind of notational convenience and notational like consistency, and we always use a capital letter for a set, then if I'm writing a really long proof that has a lot of different types of objects, I'll see a capital letter and go, okay, this should be referring to a set. And then if you're not sure, then you can go back and see if it actually was defined as a set, but it gives you this kind of idea of, okay, this is kind of what I'm working with, right? So we'll see more examples of this going on. Another thing I want to do in this class is, let's talk about this kind of notational consistency that you'll see in books, that you'll see in papers, and also just build up a set of rules for yourself as to how to write, right? So like the more consistent you are, the easier it is to write about things. So anytime we talk about different objects, we can kind of go over like, what sort of symbol you normally use for that object, right? What sort of symbol you're going to tell yourself, okay, if I see this type of symbol, what does it mean, right? If I see a Greek letter, what does it usually represent? If I see this thing, what does it usually represent? And this goes further and further. You'll see this coming up throughout the course. And when I look at stuff like this, I'll be like, okay, maybe I want to use the same letter for not just anything in set, but like if I have a prime like representative of the set, I would use this letter. But then, you know, maybe I can use like other notation for different elements of the set. It's like you'll see a lot of papers say, oh, I'm going to take A and B from this set, or people say, oh, I'm taking X and Y from this set. Well, normally you would think, oh, A and B because it's the first two letters of the alphabet, right? That's why a lot of sets, the first time you see a set defined, people either use capital A or capital S, right? Either capital S for set or capital A from just being the first letter. But in terms of like X, Y, A, B, some people just do it for O because that's what they normally use. But sometimes there is further meaning to it, right? Maybe I'll use X, Y when talking about variables I want to use later in a polynomial or something, versus I might use A if it's just an element that I want for later use. So it's not terribly important. It's not like the biggest deal in the world to keep track of like what formatting you use, but it's very, very helpful. And this is something I'll stress it a lot throughout the course because I think it's good to have some rule set for yourself, but it's not, you know, the biggest thing, right? It's just something to keep mentioning so that for those of you who are not used to writing in mathematics, this is something that you can develop for yourself. Okay, so this is our notation for being an element. Now, we talked about 5 logical connectives, right? In predicate logic and propositional logic, and we're going to apply those same exact connectives to come up with different things that we can do with sets. So before that, let me give you another way of writing about sets. So this is really just your brute force, right? You can list every single element, right? Maybe I can even say something like, you know, if I want to define the natural numbers, you guys have seen the symbol before, the first homework. Also, if I ever write colon equals, it's not just me skipping a whole bunch of empty space. Colon equals means definition, right? It doesn't mean that these two things are equal in some way. It means I'm defining this as whatever comes after. So the difference being that if I write an equal sign, equal signs have meaning, right? It depends, like, what does it mean for, you always have to ask, what does it mean for two things to be equal? Are they equal as sets? Are they equal as statements? Are they equal as formulas? And so on and so forth, right? There's a lot of different, and each of those has a different definition, right? You need to come up with a definition for equality in all those cases. But this really just, there's no point in asking what does this equal represent? It's not really an equal, this is by definition something else, right? So there's no need to like talk about this equality, right? Because it's not an equality. I'm just saying this blackboard n is defined as So this is one way you can write it. Like for us, maybe it's obvious what the pattern is going to be, but you know, those of you who are a bit more mathematically minded will go, wait, I can come up with a whole bunch of other patterns that start with 1, 2, 3. Like what do the dots mean, right? Well, you're right. This is not very standard, right? This is not going to be very formal. But whenever you see a bunch of dots like this, you're always following the most obvious pattern, right? So here, obviously, there can be a whole infinite number of patterns and infinite number of formulas that start with 1, 2, 3 and do whatever they want after that. But the most obvious thing to do is to just go one by one, right? So if you see that, really just think of it that way. But, well, maybe we can find a different way to define it, right? So this is where we want to introduce what's called set builder notation. Right. We're going to define a set almost kind of recursively, right? So I can write something like this. So again, we use curly braces for sets. These are my arbitrary objects. The colon stands for such that. Sometimes instead of the colon, you will always see some books is bar. Both are fine. There's everyone uses both. Honestly, I usually use the colon, but like I honestly do switch between both of them as well. I use colon because for me, colon represents the word such that. So like when I'm writing proofs and stuff like that, anytime I do such that, I use colons in my own notes as like my abbreviation. But both of these are fine, right? People do use both of these in set-theoretic notation. Typically, we should quantify these, right? So here we now know exactly what it means to be an element of something. Maybe I'll say x is in the real numbers, right? This is a set of all real numbers such that x is even. And obviously we all know what even and odd numbers are. And I don't want to like create some really like basic thing here. I just want to say it's even or something like that. This has its own definition, right? We'll talk about that, you know, a bit later, but when we start talking about numbers and when we start talking about maybe some elementary number theory or even before that, you know, that technically anytime you see a noun, you should define it, right? And this is something I'm going to keep stressing in the course. No matter how easy a word is, no matter how basic a word is, you should always have in your mind a formal mathematical definition. We can always find a mathematical definition of something, even though it's easy. And if you can't find a mathematical definition, that means it's axiomatically something else, but like we've said before, axioms are definitions, right? You're going to be able to go all the way back to nothing. So even is a, well, I guess in this case it's not a noun, it's an adjective, but it's still an important word, so it's something you should define. In other words, treat it like you're learning, like treat it like it's a different language, right? So if you're learning a new language, you're going to point at every word and go, oh, I don't know what that word is. I have to define it. Even if for someone who does speak that language, maybe it's a very basic word. But since you've not seen that language before, maybe you will want that word defined, right? So let's just assume we know all of the, you know, obvious words like is, and, in, right? Like obviously we know what those are, but sometimes we want to make sure that we do know what every single thing is. Like for example, this is a sentence, right? An element is an object in a set, right? And if I ask people to define or pick words to define, well, we can define what an element is, we can define what an object is, we can define what a set is, and they'll go, okay, those are the things, those are words in this sentence that I want to define. Here's the thing, you've missed this one. It looks like a really simple word, but we kind of have to define it, right? What does it mean to be in a set? We technically don't know what that means, right? So you have to be really careful and you have to challenge yourself to question the words as much as possible, right? So for example, you know, when I say x is even, you know, you should immediately be asking, okay, what is even, right? And this is something we can look at later, but this is something you should do in your own notes if you're writing something. Maybe not in note taking, but like if you're doing a homework assignment and you're writing a proof, and in the middle of your proof, you're making some claims, you're writing some sentences, always know every single word of what you're writing, right? Imagine that there's going to be some really nitpicky dude, in this case, me when I'm grading. Imagine there's going to be some really nitpicky dude coming at you and trying to like poke every single hole they can, including, oh, what is this word? What is that word, right? That's how you want to kind of remember to work with your definitions. Right, the whole point of math is, you know, like I said the other day, math isn't about creativity, but even more so than that, it's not so much that math is not about creativity, but rather math is about just definition tracing. That's all math is. It's math helps us build a language where we can understand more complicated things, right? And we've kind of designed this language and optimized this language to the point where we can talk about anything, right? We have ways to talk about really abstract things. But because of that, it's really important to know the language well. So this is kind of what we're stressing in here. But back to set-theoretic notation, you know, this is kind of thing you'll see, right? So in here, you'll have, you know, this is a set of some values. You can talk about what set it's from, such that some property is upheld, right? So using terms from propositional logic, we can even say some x in the universe. Right, so now this is using terms from propositional logic, right? And maybe here, this in symbol we can also use from propositional logic. It's something from a universe that we've already defined, right? So that's set voter notation. So what I'll do is on the homework, I'll probably give you a couple of examples. I'll give you a set maybe written out in this format, or I'll give you some formula or something, and I will maybe want you to write out what that set is without using formulas. Well, without using that specific formula, but somehow writing it in set notation, because obviously we can have equations in set notation. For example, this is a really dumb thing, but I've written this in set notation. But what is this? This is just a set containing 1, right? These are the same set. I just wrote it in set notation. I'm going to change this to natural numbers. Still the same thing, right? Obviously, there's more than one way to show something in set notation, but that's kind of just how it should look. Okay, so those are the 2 ways we represent sets, right? Any other way will be more arbitrary when we talk about sets in comparison to other sets. Or maybe we want to talk about set more abstractly. But now let's go back and dive in and create some set operations, right? So what I'm going to do is let's kind of have a table where these are our logical connectors. And these are set operations. Right, and by the way, when I use the word operations, I just mean things that, you know, it's a term we use in math to denote something that does something else, right? You operate on something. That's kind of the notation we use. It doesn't mean anything specific. It's just typically we'll use operation to refer to like things we do to combine other things. Okay, so if you guys remember, we have 5 logical connectives. We have the disjunction, we have the conjunction, we have the negation, forwards implication, right, the conditional, or the biconditional. Right, so we're going to create set operations for each of these. So the first 2, I'm just going to kind of smooth those out, right? A lot of you have seen this before. It's called the union. It's called the intersection. Right. So before I formally define it, let's draw a picture for each of them. And this is something I'm going to stress a lot whenever we see something a bit more complicated in set theory. And maybe even when we're using set theory within other fields of mathematics, which it obviously comes up a lot. Obviously, drawing a picture is not good enough for proof, right? If I want you to write a proof, I want you to mathematically tell me why what you're saying is true, right? Just drawing a picture and saying, look, this picture represents the question. I mean, I'm not sure that's correct, but I want to see it more formally. But that being said, a lot of the time, being able to draw a picture helps you understand what's going on. So it might be useful to draw pictures for yourself before understanding what a definition is trying to say, right? And this is something I do a lot. You know, in terms of problem solving, if you can't draw a picture somehow to illustrate what you're trying to explain or to illustrate what you're trying to understand, that means that you don't understand what's going on, like intrinsically, right? A lot of the time, if you're not able to draw a picture, it means that you don't really know what's going on. And I always recommend making sure that you know how to draw a picture for a definition, or making sure you know how to draw a picture for something before moving on and going, further in writing up mathematics or something like that, just because the picture helps you kind of get a feel for what you are doing. And this is something in terms of the kind of like the problem solving aspect of this course that I'm going to reiterate this, right? Like before you even start doing the problem, draw a picture, see if you can understand it, right? It's almost like, you'll get this line like word problems in like elementary school or something. It's like, oh, okay, here's one way to solve the word problem. You draw a picture that represents the word problem and you go from there, right? Because sometimes it's easier to see visually what's going on. And this is even more true in like proper mathematics, right? It's not part of your actual proof, but it should be something you do. So in that note, before I define anything here, I'm going to go ahead and draw a picture for each of these, right? So these are operations. Let's look at here. The conjunction and disjunction, right, happen for connecting two statements. So in here, we'd expect them to connect two sets. And when we talk about sets, right, the easiest way to do it is by a Venn diagram. Where this is the set A, and this is set B. And by these Venn diagrams, I think it's probably obvious that when I draw a circle and label that a set, I'm saying that all of the elements that you find in the set are exactly the ones in here and only the ones in here, right? There'll be a bunch of dots in section A, in set A, and those are in there, everything else is outside of it, right? So the idea being that the union is all of this, right? And in the intersection, it's probably equally obvious to see, right? And we can kind of compare this to the truth table, right? Here, only A is true and B is false, right? So I can almost think of it, if we want to think of this as where the statement is true and where it's false, this section indicates A and not B somehow, right? Obviously, usually when we define a negation, we can only negate statements, but B is a set. So maybe this isn't good notation, but that's another thing I want to stress is this is why it's important to talk about what types of mathematical objects we're looking at, right? So, when I say negation, I'm not just saying, oh, I negate something, right? I'm specifically saying I negate statements. These aren't statements, they're sets. So a priori, this doesn't mean anything. For now, I'm writing that just to give you an idea of what's going on, right? But maybe it will be easier or more formal to say, let P be the statement, or sorry, some predicates, I guess. Let P be the statement that X is in A. And Q be the statement X is in B, right? So then anything in here represents X such that now this is fine, right? And we can keep going on to see that, okay, this is P and Q, this is not P and Q, right? Those are all true. The only thing I have gotten rid of is not P and not Q from outside. So this matches the truth table that you guys have seen for the disjunction, right? So now we have this for union. And same thing for here, right? The only place this is true is if both of them are true at the same time, right? Okay. So negation, well, we talked about how we can't negate a set because we negate statements. So let's talk about the analog here. It's a C for complement. And I write it small because usually this is a superscript, right? So it's a C or something like that. There's a few different notations for this. This is probably the most common just because C stands for complement. Some books especially those for like introductory set theory for like freshmen in like maybe your college algebra or college mathematics for liberal arts majors. You'll see this, right? Not a one, but a prime, right? Where prime is that same like apostrophe thing. This can also recommend complement, right? This is the standard notation in proper mathematics, but you also see this. It's not wrong to use that. Just be consistent in what you do, right? I would recommend that you just use AC so that you just know C is the complement. Now, there's two ways we can talk about it because there's an issue here. In this case, we talk about negation, right? So in the negation, we say every statement is either true or false, right? So then we say that if I take a statement, the negation is you flip it to the other case where the true statement where it was true before, now it's false, where it's false before, now it's true. We're going to do a similar thing with the complement, but we know it doesn't make sense to say a set is either true or false, right? But we can say, we can divide our universe. Again, I'm going to use this term universe to divide out things from the set versus things which aren't in the set, right? So we can say the complement is made up of everything that's not from the set. Now, when you say everything, you have to be careful, right? Because again, we have to define what universe we live in. So we should define what we call a universal set. Right? This is the set containing all the relevant elements. Because when I say a set is a collection of objects, I could easily have said, oh, I have a set containing letters, right? The set, if I have this set, this is still a set, right? But if I'm talking about, maybe some mathematical formula, I maybe don't want sets like this, right? So maybe I want to restrict my universe to numbers. I want to restrict my universe to row numbers somehow. Or if I'm talking about words, maybe I want to restrict my universe to letters. So for example, if I want to treat the dictionary as a set of all possible words, maybe I want, and maybe I treat each word as a union of letters. Maybe I want my universe to just be made up of English letters, right? And different combinations of English letters. I want to exclude numbers and stuff like that, right? So we want to be careful in defining our universe because we need this to talk about some of these guys. And you'll see this U come up when I'm talking about definitions for some of these things. Okay, now implication, right? Actually, yeah, let's draw this. So I'll kind of draw this box to indicate the universal set, right? So for each of these guys, you can imagine there's a box around it. For example, here, where this is a universal set. So everything is not in here, it's just everything that's in the box, just not in those two. All right, so this is my set A. The complement is obviously, right, I should say, right? Notice I didn't give the negation as one of the possible ways to talk about that. Some people do in statistics. I disagree with this because negations are used for statements, complements are used for sets, so they act on different things. This is what we're looking at. Okay, so implication. We've kind of had this similar discussion where if A implies B, that means if I'm in A, then I'm in B, and we kind of drew this picture for, okay, here's A. Well, what's the only way that being in A necessitates you also being in B? And draw it on the outside, like that, right? Well, here's how we create this operation. This is a subset. And you'll notice that if you read a lot of different set theory books, and if you're trying to learn this on your own, a lot of people just introduce these operations by themselves, right? Which is totally fine. We can talk about all the operations you need in set theory just by themselves, and that's fine. But I want to give you this comparison because there really is a reason how we came up with these operations, right? We came up with these because we are building sets to play with logical connectives in a different setting. Now, instead of statements, we're using sets. So anytime we have a logical connective to talk about our statements, how we put statements together, I want to have that same way to talk about sets, right? So it might be natural to think about subsets because, oh, I want to think about different things inside my set. That might be one way to think of it. But the way I like to think of it is because, well, we need a way to discuss the logical connective of the condition, right? So that's how we do it. So we just use a subset. And finally, if you go back and forth both ways, this is where Kamal asked something the other day. It's a very good question. Does this mean they're the same thing? Well, a priori, no, but it has a similar idea, right? And since this is a similar idea, we're going to define it this way: equality. So one way to define equality is we can say two sets are equal if they contain all the same elements, but we're not going to define it that way. Some books will define it that way, but I think it's not as clean to do so. And I think it's better to define it using what we have over here, and we'll start building that. So now that we have each of this, let's write out our definitions. So right now, I'm not treating this as, just performing some operation. I'm saying that I claim this is a set, right? I claim that if I have sets, so we'll say let A and B be sets from U, where U is a universal set, right? That's not the union. It's kind of unfortunate that they look the same. I'll just say U is this is the universal set, right? So we can define A union B using set builder notation. So this is all X of U, right? This is where we need the fact that this is from the universal set. We're not just looking at X in general, right? We're allowed to, so kind of use the same analogy, right? When we're talking about predicate logic, I said when you say for all X, we don't write this symbol because we haven't talked about it yet. We're not talking about sets, we're talking about statements. But we have a domain, we have a universe within everything this. So when I made a statement like for all X, for all Y, some P of X comma Y, right? In predicate logic, I have a universe within which X and Y live. And this is my universe here. So in set builder notation, I'm going to say X comes from that universe. A or right, you can see why these two are related. Another thing I want to note here, you can, for your own notes, you can use abbreviations like this, where when you read this in English, you would read this as the set of all x's such that P of X is true, right? That's totally fine. But if you want to write it out formally, I would always recommend that you write it as belong to something. So this kind of builds your intuition and it builds your mathematical formality in telling me where that element lives, right? Does it live in certain universe? Does it live in row numbers? Is it in letters? Blah, 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 right? So it might be obvious where it should live, but let's make sure that there's beyond a shadow of a doubt a set that we know this thing comes from. And that's why I'm going to do it. Okay, so as you can imagine, let's find this set. Find it very much the same way. Right, so now all I've done is, if I already have two sets, I know how to take things out of that set. So when I define a union and intersection, I'm only using these logical connectors, right? Because these are statements. By saying X is in A, that is a statement given that I already know where X is from, right? So these are statements within predicate logic. Then now A, set of all U such that. So there's two ways to write this. right? If I want to be really strictly formal, we talk about how this can be a statement in predicate logic, and I just negate that statement. This is not how we normally write it in math. How we normally write it instead of all x's from the universe that are not in A. So all of you have seen basically throughout your life that this is the equal sign, this is the not equal sign, right? That's inequality, you guys all know that. We're going to use this exact same thing for any other operation, basically. Basically, any operation, you just put a line through it, and it's the opposite of what it meant. So much so that in LaTeX, so this in produces this symbol. If I do this, the backslash not literally reads what the next symbol is and puts a line through it. But basically anything, right? Technically, I can do this, right? I can write not and an equal sign, and it will do this, but you don't have to do that. This has a natural any key, right? But really, any symbol, if you want to put a line through it, you can just use the backslash not in front of it. Because that's just a notation we're going to use, right? We either have an operation or things that don't follow that operation. So this is how we normally write this, right? X is not, and we read this as, this is a set of all x's from the universe such that x is not in A. So that's the negation of A. Okay. A is a subset of B, right? So I'm not going to define it as a set because this isn't a set, right? This is I'm relating two different statements, right? So here in the implication, I am creating new statements, but it's more so that I'm talking about two different things, right? So we say that A is a subset of B if they're all X and A. So now we're going back to this whole, quantifier statement thing where I start with a bunch of quantifiers and I end with a single statement, right? If I wanted to write this in proper predicate logic, we can say that, oh, for all this, we have this. So if for all x, p of x implies q of x, you can say something like that. But we can easily write it this way, where we can read this as for all x's in A, we have that x is in A. Right, so that's the definition. Now, finally, how do we define equality, right? We define the biconditional by saying that, oh, this is the forwards and the backwards, right? This will say A equals B if A is a subset of B and B is a subset of A. Right. So we define two sets to be equal if they are both subsets of each other. And this should make sense, right? This is exactly what Kamal was saying the other day. If I'm drawing A like that and a B like that, right? This means A is a subset of B, but how would I draw the picture that B is a subset of A? I need B to be inside A in the same way. So the only way to make that work is make them the same circle, right? Or make sure this thing is basically non-existent, is empty. Right, so we have those definitions. So now that we have definitions, this is the first thing I'm going to formally say about proof writing, right? Whenever you're writing a proof and I'm asking you, hey, is this thing true? Is that thing true? The only thing you have to work with is the definitions, right? So if you want to prove something is true, you have to follow the definition to show that it's true. For example, if I give you two sets and I want you to show that one is a subset of the other, you don't describe it using a picture. You don't say, oh, I picked something, it's obvious that this is another thing. You don't do that. You follow this, right? You follow the definition. In other words, to prove that A is a subset of B, you're proving this statement. If you want to prove that A equals B, you're proving this statement, which now amounts to proving this statement and this statement at the same time, right? So this is where we'll start seeing proof concepts. And before asking you to write a proof, I'll maybe show you some different ways of writing proofs. I'll maybe give you guys a few examples. I might set, so probably in the homework, I haven't decided what's going to go in the homework yet for Friday, but what I'll do is I'll probably give you a couple examples of what a proof should look like. And maybe you guys can do simple proofs that are similar to those. But this is kind of the first place I'm going to start stressing, how we prove this, right? You've noticed that I stress definitions a lot, and that's for good reason. Definitions are what you use to build everything. So when you're writing a proof, you need definitions. Okay. All right, so these are all the definitions we need for set operations. Let's see. So I want to, as an aside, talk about maybe, let's see. So I told you at the very beginning when I defined a set, we said that, oh, it's a collection of objects that maybe satisfies a certain property, because it could be anything we want, right? If I could say, pick the set of all people who are wearing a shirt, or pick a set of all people who are wearing a red shirt, or pick a set of all people who are male and wearing a red shirt, right? All these are possible. I can put properties that I want. But we have to be careful when we say any property. So let A be defined as set containing all, I'm not even going to define this. And I'm not even going to define this. We'll be very loose, right? We're going to ask the question, can I have a set of all sets? So the immediate thing that most people say is, well, I'm allowed to just provide a property. So yeah, this is a set. But here's the problem. So let's just call this S, capital S, right? And let's just say S is the set of all sets, right? So if I pick out an element in S, this should work, right? So maybe let's let A be defined. How do I want to do this? Let me see. Do I want to do this? There's a standard thing to do here. I want to see if I want to deviate from that. I probably don't want to deviate from it. Just want to make sure I can. Let's see. Yeah, I think I want to deviate from it because this probably takes too much. Yeah, if I deviate from it, that's going to be a bit complicated. So I'll just give you the standard thing, right? I'll just go back and give you the very standard thing that most people do for this example. Let's just let R be the set of all sets such that not an element of itself, right? Because if I can just use whatever property, then sure, I can say this is a set, right? Because now this is a property I can write using, it's just basic logical connectors. So the question is this a set, right? Well, let some set A be in R, right? Then, that by definition, since A is in R, A is not a set of itself, right? And so we can kind of go forward and say something about this. So what can we say about it, right? We're essentially claiming that there's going to be an issue here, right? So if you guys think about it, we can sort of see the issue being that this whole weird thing of a set not being able to be in itself will give us some paradox, right? And this is called Russell's paradox. So you're going to have some issue where you can contain both sides, right? We claim that when we define what it means to be in a set, we still have that, we have that these two are completely opposite ideas, right? In and not in, they're completely different. So basically, sorry, I think I messed something up here. Sorry. I want to do this a bit differently. I want to use that notation. I'm trying to use notation without getting too much beyond what we've talked about so far. So I'm going to write this. I think this is probably better notation to use, right? So notice that if we write this, we can ask, is R contained in itself, right? We then have that if R is contained in itself, R is a set, it doesn't follow this property, so R is not in. Sorry, that's the real numbers, it's not what I meant to write. Right, whereas if R is not in R, that means it is following this property, right? This implies that R is in R. But we've already defined these two things, right? We've defined the fact that these are subset kind of things. So this, because I've gone both ways, this can become an implication. So R is in R, it can only if R is not in R. But this is obviously impossible. We already know that this thing, right, this symbol means the exact opposite of this symbol by definition. This cannot be true. So we have a contradiction. And we'll talk more about what this means in a little bit, right? This is what we call a proof by contradiction. We'll talk more about that in proof techniques. But the idea is we assume that this was a set, because note that everything I've been talking about here assumes things that we use in set theory, right? This is a operation sets, we're assuming these are operations in sets and so on. So the only assumption we've made is that this is a set. That was no assumption, right? And we get something that just totally doesn't work. So the contradiction tells us that, oh, this could not have been a set, right? So what this says is that there is no set of all sets. That doesn't exist, right? Later, when we get into the category theory section, we'll talk a little bit about how we get around this issue. Because obviously, it's nice to talk about something, some object that contains all sets, right? You can almost think of like, okay, sets kind of like allowing you to form these nice circles. What happens when you kind of try to go bigger than that, right? Can you find something that contains everything you want to talk about, right? So there's a way to do that we'll talk about later, but for now, this basically just tells you, oh, we can't just talk about a set and just put any property we want on it, right? We want to be able to know for sure that it is a set. So this is just showing you that you have to be careful with defining a property, but for the most part, anything's going to work, right? As long as you have some statement that doesn't break anything, right? If it works as a regular statement, then you should be fine. The main issue he was picking something weird, like something not being itself, right? So. Okay. What I'm gonna do is, let's see, how much time are we at? Okay, so I think I'll just talk about some types of sets and some examples of sets. So some examples of sets. This is what we call the empty set. We can also write it like this. It's a set containing nothing at all, right? And it sounds stupid to talk about, but just like we need the number 0, we need an empty set. And in fact, if we talk about number theory, in fact, if I talk about like, if I want to be more formal with talking about set theory, I can even say that, oh, we don't know what numbers are. We don't even know what 0 is. But we do have an axiom that tells us there must be an empty set. This is an axiom. The fact that there exists an empty set is just axiomatically defined. Maybe we can even define the number 0 using the empty set, right? And when I finish up set theory tomorrow, I think I will maybe give an example of that. Right? I'll maybe give an example of how we can use the empty set and only the empty set to construct all the numbers we have. But for now, we'll think about this as this. Caution. We talk about sets you have in curly braces. This is not the same as this. This is a very common mistake that a lot of people make, right? Turns out that this is an element of this, right? Because it is something I find within the curly braces here, right? This thing is, and it looks stupid to write, but that's exactly what it is. It's a set that contains a set that contains nothing at all, right? So when I put extra curly braces around something, those of you who are in comp sci will say, oh, that doesn't do anything. And those of you who are literally writing in LaTeX will say, oh, if I put a bunch of curly braces around something, it's not going to change what I print out. That's correct in terms of writing. But when we talk about set theory, adding more braces changes what you're talking about, right? So if I add another set of curly braces here, that's again not the same thing. So be very careful about how you write this and make sure you recognize that these are not the same thing. Another important set to know is what we call the power set. So let X be just a set. The power set of X and I'm not very good at writing in like fancy letters or fancy fonts on the board, but this is there's like a script P or script capital P that you'll see. If you look up power set on Google, you'll see the symbol that they normally use. In LaTeX, instead of mathbb, you can use mathcal, right? CAL. This will output the usual P that we use for this. There's another package that you can get that you can use math SCR for script instead of mathcal, but I prefer mathcal for this. But okay, so what is the power set? The power set is defined as this set of all A such that. And technically here, when I don't write anything else, I imply that A is in my universe, right? You can write that A is in U, where U is the universe of all possible sets, right? Now notice I didn't say set of all sets. The universe might not necessarily have to be a set. In fact, in most cases, the universe is not a set, right? You can talk about a universe that contains all possible sets, and that's fine. A is from that universe. But here, I'm just saying that A is a set of all subsets of X, right? So example. X is 1, 2, right? What are all the ways in which we can find a subset? Now, instead of just writing them out, we can immediately, we can look at using a process, right? There's 2 elements, 1 and 2, right? And when we form a subset, we only have 2 choices for each element, right? As we talked about, either the element is in the set or the element is not in the set. So right, so these are all the possibilities, right? So let's write out all these. So first of all, the power set is a set, right? What's the first element of the set? It's an element that contains both of these. Right. This one is a set that contains 1 but not 2, so it's just a set 1. And then the other one's just a set 2. But then what about the one that doesn't contain anything, right? What do we call a set that doesn't contain anything? We call it the empty set. And notice I didn't put curly braces around the empty set, right? Because I could have just as easily written this without putting a 1 or 2 in it, right? But that's the same way we define this symbol to be the empty set. So what I just wrote here is a power set of the set containing 1 and 2. So some properties of this. The empty set is always contained in the power set of X. And X is always contained in its own power set, right? Those are pretty much obvious. These are always going to be there. We might not have an easy way to write the rest of them, but we know at least for a fact that the empty set and X itself are going to be in the power set of X always, right? Okay, so this is another thing we can talk about. Let's see, what are some other things? Okay, so I'll talk about, I was trying to decide if I want to talk about like the size of a set. I'll leave that for tomorrow where we can formally define that. We'll talk about sizes of sets tomorrow. We can use power set as an example. So now let's just end this with, let's talk about some of the types of sets that we normally use in mathematics, right? The more common sets, the ones you've seen with this Blackboard font that I talked about in the first one. Right, so we start with the natural numbers, right? So we said that this isn't quite formal, right? But we can say that let 1 be here. We're going to construct this set. For now, we're going to assume we know what this plus is. We're going to assume this plus is the same plus that we use in high school. We haven't defined it yet, but I'm going to assume we've defined it already, right? Just think of like 1 plus 1 is 2, right? We know what that means. Technically, we don't know that yet, and later on, I can maybe show you how we can think about this, right? I can show you ways in which we can talk about what plus means, how we can get the next, what does it mean to take the next one, and so on and so forth. That's a very big part of set theory. I still haven't decided if I want to cover that tomorrow. I think I will, just to show you guys how it works, but we'll see if I have time. But for now, you can think of the way to create the natural numbers as you start at 1, and then you just have this condition where if something's in a set, the next number, if I take plus 1, it's also in the set. So this is a bit hard to define, but we'll see how we define it tomorrow probably. So now the integers, right? The integers are the set. When I usually say integers, you guys usually know what I mean. Right? It's all negative natural numbers, including 0. I can also say this is equal to set containing 0 union the natural numbers union the set of all negative x such that x is n. Right. This thing, if you ever see just a negative of a set, canonically or by definition, this is what we mean, right? when we take the negative of a set, we can only do this for sets that contain numbers, or for sets that negative has a meaning for the elements, and we just say this is a negative. Right, so that's one way you can describe the integers. Okay, so now we have the rational numbers, right? And this is defined as the set of all A and B such that A and B. Okay, so now there's something I want to say that I forgot to say earlier, and this is that sets can contain multiple copies of unique elements. What do I mean by that, right? So if I say, hey, I want a set containing 1, 2, 2, 3, right? This is not a set, right? Because each unique thing can only appear once in a set, which is probably what I forgot to mention earlier. We might call this a multi-set. Some people use that term, where a multi-set is one where I'm allowed to put a number in multiple times for various reasons. But typically for a set, we define it as, everything can only appear once, right? So if I have a bag of 10 marbles where 9 are red and 1 is blue, and I want to write out a set of the colors, I'm not going to write the word red 9 times and then blue 1 time. It's just going to be set red, comma, blue. That's all. Right. For a multi-set, maybe you write it multiple times for certain reasons, especially probability, but we're not going to go into that. We're just going to say everything's included once. So on homework 1, when I talked about the rationals, maybe I defined the rationals as taking every single fraction that's already in lowest terms, right? The reason we say lowest terms is because then you get stuff like, okay, maybe 2 out of 4 and 1 out of 2 are things from this set, right? So if we just stick with these being real numbers, then these are the same thing, right? They represent the same number. They both represent a half, right? But if we're just writing this as numbers, if we don't even think of these as real numbers, if we just think of them as something over something, then 2 over 4 is not necessarily the same as 1 over 2. And that's why sometimes we require the condition that the GCD, or the greatest common divisor of A and B, is 1, so that we avoid this happening, right? If we include this condition that the greatest common divisor is 1, we don't have to worry about this case where these are 2 different objects in the same set that represent the same number, right? But you can easily get around this by, you can get rid of this condition by just saying that these are real numbers, but I don't want to do that for now, right? We're just defining this using just fractions, right? Just some number over some number without any other meaning to it. For now, I'm not going to define what real numbers are, because it's actually very difficult to construct the real numbers, right? There's quite a difficult construction, because real numbers are just all the rationals and all the irrationals, right? But typically we'll define irrationals as being numbers that are not from real numbers that are not rational, right? So for now, we'll just say real numbers are what we think they are. In terms of constructing them, we'll have to do that much later once we have more tools in our toolkit. And here's another one that a lot of you will see. These are complex numbers. Right. This is the set of all A plus BI such that A, B are real, right? And I squared equals one. Right, so that's a condition we use to construct the complex numbers. It's easy to see that most of these are subsets of one another. These form a chain. The one that's maybe not so easy to see is you might say, oh, the complex numbers have 2 things to it. A real number will only have one thing to it, like 5, right? I claim that R is a subset of the complex numbers, and a lot of people go, oh wait, why is that true, right? I have two different arguments here. Well, the idea is that, well, just let B be 0, right? 0 times anything is still 0, or we at least assume so. 0 is a real number. So if I want to write 5, I can instead write it as 5 plus 0i, right? So R ends up being a subset of the complex numbers, right? So essentially, we get this chain, right, from all these definitions. These are the very common sets you'll see in terms of just working with mathematics in general. And this is kind of why we start with set theory, is to build ourselves a language that allows us to talk about these sets. So these form a chain of sets containing each other. Well, not each other, but sets containing one previous. Okay, the final thing I'm going to talk about today, I should have probably talked about it when I was talking about different properties. It's similar to negation, but not quite. So A and B, these sets from some universe. There's two definitions I'm going to give here. These are other properties that we came up with that are not based on the logical connectors. So there's two main ways that people write set difference. Difference in math usually means minus sign. So some people will write this as A minus B. What does it mean to subtract two sets in some way? This is the more common notation. This is a backslash. For those of you who are trying to write this in LaTeX, you'll go, wait, backslash, just if I type that, it tells me to write a command. But then I also told you that if you want to write a symbol out that's not usually simple, you do something like backslash curly brace, right? But then the problem here is if I write the double backslash, it just starts a new line for me. So the way you would produce this is just by writing backslash, which is really hard to say in words, but that's what you would do for the symbol. So these are two ways you will see this set written. The minus sign, like on paper, it's going to look different than the regular minus sign. It looks a bit bigger, it looks a bit longer. You want to see what it looks like, you do this as set minus in LaTeX, right? So you'll see that it's kind of prints out a slightly bigger minus sign just for sets. How is this defined? Well, this is exactly the set of all things from U, such that X is in A and X is not in B. And the way I can write this right. Be careful here. There's no parenthesis, so this is really technically this is in parentheses by itself. Right. And maybe this is a good time to talk about order of operations, because when I wrote this was fine. So the order of operations goes, I always do my complements first, and then I'll do my unions and intersections, and then I'll do implications, and then I'll do equalities finally. And then if everything is the same priority, I'll do left to right. Right, almost like your PEMDAS kind of stuff, right? But basically, same kind of idea. Right, but always do complement. Obviously, if something's in parentheses, do it first. But complements will be done before these. So right, so when I write this, I can't interpret this as A intersect B complement because that's something different. The last thing is, instead of talking about set difference, we can talk about the symmetric difference. And now, thankfully, we don't have a different symbol for this. We don't have two different symbols for this. We just have this. And yes, in LaTeX, you can literally just write backslash triangle, like the word triangle, and that will produce this. So this is a set difference. Let's kind of draw this out first, right? What is A without B? It's this stuff, right? It's A intersecting everything that's not in B. So now for the symmetric difference, this is A and this is B. That's this stuff. So in other words, I could write this as A without B union B without A. Right? So that's what the symmetric difference is, if you ever see that. Okay. And I guess one more note that I don't really want to talk about tomorrow, since it's not really a big note. We'll notice that we combined, also rather, when we talk about our logical operatives, right, we kind of have related them to sets in terms of we have negations are complements, unions are unions are disjunctions, intersections are conjunctions, right? So last thing I'll note is, do you guys remember we talked about De Morgan's laws for propositional logic? Well, we have De Morgan's laws for sets that work in exactly the same way. We have a complement, which is A complement intersect B complement. A intersect B complement is equal to A complement union B complement. This works in the exact same way that De Morgan's laws for logical connectives did, in the sense that when we're taking a complement or a negation and we're distributing through everything else, we just flip everything, right? So maybe it's, using our definitions for what a union is, for what an intersection is. Maybe you guys can prove, and maybe I'll give this as a homework, prove that one of these equalities is true using only logical connectives, right? So, and you'll see that it literally works because their analogs work in propositional logic. So I think that's where I'm going to stop today. And then tomorrow we'll pick up with a few more things on sets. And then maybe I might talk about a couple of proof techniques, and that will end our little 2-lecture portion of set theory. Okay, if there's no questions, then I will see you guys tomorrow.